So let's do this infinite square spherical well. Now, the reason we did the free particle first was that inside here, this is all free, so the solutions will be sort of simple. Nevertheless, we can begin with looking at the differential equation directly for inside. So r less than a, you would have minus d second UEL over d rho squared, actually, plus L times L plus 1 over rho squared UEL equals UEL, where rho is equal to KR. And K, I'm sorry, I didn't write it. There is 2ME over H squared, as usual. So here, I didn't say what K was. That was 2ME over H squared. And this doesn't quite look like the differential equation you have here. Well, V of r is 0 for r less than a, so you just have this term. The h squareds over 2m and the e have been rescaled by changing r to rho. So the differential equation becomes simple and looking like this. So that was a manipulation that was done in detail last time, but you can redo it. Now, this, as I mentioned, is not a simple differential equation. If you didn't have this, it would have a power solution. If you don't have this, it's just a sines or cosines. But if you have both, it's Bessel. So having a differential equation, two derivatives, 1 over rho squared and 1, brings you into Bessel territory. Anyway, this is the equation that, in fact, is solved by these functions, because it's a free Schrodinger equation. And you can take it for L equals 0. This is the only case we can do easily without looking up any Bessel functions or anything like that. You then have the second U E0, the rho squared, is equal U E0. And therefore, U E0 goes like A sine of rho plus B cosine rho. Rho is KR. UEL must behave like r to the L plus 1. So UE0 must behave like r. So for this thing to behave, must behave like r. So it must behave like rho as rho goes to 0. Therefore, this term cannot be there. The only solution is UE0 is equal to sine of rho, which is KR. So UE0 of r must be of this form. Then, in order to have a solution of the one-dimensional Schrodinger equation, it's true that the potential becomes infinite for r equal a. So that is familiar. It's not the point r equals 0 that is unusual. R equal a, this must vanish. So we need that u E0 of a will equal to 0. So this requires k equals some kn, so that kn a is equal to n pi. So for k is equal to kn, where kn a is equal to n pi, a multiple of pi, then the wave function will vanish at r equals a. So easy enough. We've found the values of k. This is quite analogous to the infinite squared well. And now the energies from this formula, En, will be equal to h squared kn squared over 2m. And it's convenient, of course, to divide by ma squared, so that you have kn a squared. So the energies are h squared over 2ma squared. Here we have n pi squared. I'll put them like this, En 0 for L equals 0, ENL's energies. Now, if you want to remember something about this, of course, all these constants are kind of irrelevant, but the good thing is that this carries the full units of energy, and you know in a system with a length scale A, this is the typical energy. So the energies are essentially that typical energy times n squared pi squared. So it's convenient to define, in general, ENL to be ENL for any L that you may be solving, divided by h squared over 2ma squared. So that this thing has no units. And it tells you for any level, the calligraphic E, roughly how much bigger it is than the natural energy scale of your problem. So it's a nice definition. And in this way, we've learned that En0 is equal to n pi squared. And a few values of this are E10 about 986.96, E20 equals 39,478, and E30 is equal 88,826. Not very dramatic numbers, but they're still kind of interesting. So what else about this problem? Well, we can do the general case. The general case, let me erase a little here so that we can proceed. The general case is based on knowing the zeros of the spherical Bessel function. So this is something that the first one you can do easily. It's sort of the zeros of J1 of rho are points at which tan rho is equal to rho. That's a short calculation if you ever want to do it. That's not that difficult. Of course, but you have to do it numerically. So the zeros of the Bessel functions are known and are tabulated. You can find them on the web. Little programs that do it on the web and give you directly those zeros. So how are they defined? Basically, people define ZNL to be the nth zero with n equals 1, like that, of JL. So more precisely, JL of ZNL is equal to 0. And all the ZNLs are different from 0. There's a trivial 0 at 0. And nevertheless, that is not counted. It's just too trivial for it to be interesting. So these numbers, Z and L, are basically it. Why? Because what you need is, if you're looking for the Lth solution, you need UEL of A equals 0. And UEA of that equals 0 means that you need KNL times A be equal to ZNL. So KNL is the value of K. And just like we quantized here, we had Kn. Well, if you have various L's, put a KNL. So for every value of L, you have KNLs that are given by this. And the energies like this. Let me copy what this would be. ENL would be ENL over this ratio. And ENL is H squared. Well, let me do it this way. I'm sorry. ENL would be H squared KNL over 2MA squared. Over 2M, like that. Then you multiply by A squared again. So you get KNL A squared over 2MA squared. So what you learn from this is that ENL, you divide this by that, is just KNL times A, which is ZNL squared. So that's the simple result. The ENLs are just the squares of the zeros of the Bessel function. So you divide it again by H squared over 2MA, and that's all that was left. So you need to know the zeros of the Bessel function. And there's one, you might say, well, what for do I care about this? But it's kind of nice to see them. So Z11 is equal to 449. Z21 is equal to 772. And Z31 is 1090. Numbers that may have no rhyme or reason. Now you've done here L equals 1. Of course, it continues down, down, down. You can continue with the first zero, first non-trivial zero, second non-trivial zero, third non-trivial zero, and it goes on. The energies are the squares. So the squares squared goes like 20, 1, 9. This goes like 59.7. And this goes like 119, roughly. Then you have the other zeros. First zero for L equals 2. That is 576, roughly. Second zero for L equals to 2 is 9.1, roughly. And if you square those to see those other energies, you would get, by squaring, 33.21 and 82.72. And finally, let me do one more. Z13, the first zero of the L equals 3 and the Z23, the second zero, are 699 and 10.4. which when squared give you 48, 83, and 108.5. Okay. Why do you want to see those numbers? I think the reason you want to see them is to just look at the diagram of energies, which is kind of interesting. So let's do that. So here I'll plot energies, and here I'll put L. And now I need a big diagram. Here I'll put the curly energies, and here is 10, 20, 30, 40, 50, 60. And now I need the next blackboard. Let's see. We're 60. Let's see, more or less here, is that right? 70. 80, 90, 100, 110. How far do I need? 120. Ooh, okay. 120. There we go. So, just for the fun of it, you look at them to see how they look, if you can see any pattern. So the first energy was 986, so that's roughly here. That's L equals 0. It's the first state. Second is 3947, so it's a little below here. Next is 8882. So we are here, roughly. Then we go L equals 1. What are the values? This one's 2019. L equals 1. 2019, so we're around here. Then 59.7 is almost 60. And then 119, so that's why we needed to go all that high. So here we are. And then L equals 3, you have 4883. So that's 50. No, I'm sorry, L equals 2. 4883. It's a little lower than that. And then, I'm sorry, it's 3321. I'm misreading that. 33 over here. And then 82.72. So we're here. And then L equals 3. We have 4883. So that was the one I wanted. And 108.5. Okay. That's it. And there's no pattern whatsoever. The zeros never match. The only thing that is true is that 0, 1, 2, 3, they were ascending as we predicted. But no level matches with any other level. You know, if you were trying to say, OK, this potential is interesting, is special, it has magic to it, a spherical square well. It doesn't seem to have anything to it, in fact. It's totally random. I cannot prove for you, but it's probably true and probably not impossible to prove that these zeros are never the same. No L and L prime will have the same zero. So this is a totally, no degeneracy ever occurs that this needs an explanation. For example, this state could have ended up equal to this one or equal to this one, and it doesn't happen. And that's okay, because at this level, we would not be able to predict why it happened. We actually, apart from the fact that this is a round, nice box, what symmetries does it have, that box, except rotational symmetry? Nothing all that dramatic.